Okay, is it about time? I'm not sure.
Yes, it is. It's 3 o'clock.
All right. Okay.
We have one question.
Yes, I saw it. Alexa, right?
Yes.
Yeah, because if you, so you say the penetrance, they don't need this, they do. In other words, an individual has to have one of those 3 genotypes. So you have to make it so, first of all, given the genotype, then you have to adjust the likelihoods to make the 3 add up to 1 always. The summation over genotypes has to equal 1 always. Always.
But yeah. Wouldn't that make sense for the probability of the genotype? Not the penetrance.
Oh, gee, if I got it wrong.
I remember programming this, just not how it, how it went.
Oh, you programmed it years ago?
Years and years ago in the old version.
Oh, I wonder who had this idea. I thought it was Kevin Jacobs. Obviously, it wasn't.
Oh, it could have been. Oh, no, not Kevin. Not that Kevin.
Not that Kevin.
Maybe Alec.
It might have been Alec. Yeah. So I don't know. They don't need to sum to 1, do they? You have to standardize these things. That's all I can say at present. You have to have 3 things that add up given. Yeah, it has to have one of the 3 genotypes, right?
Right, but in the same file you have a probability of each genotype, but that's a different number from the penetrance part.
Yeah, but oh, I don't know. I'm too tired. We'll have to think about it. And you say you programmed it, so you know.
Well, long ago.
I don't know, but I know it works, whatever it does, but I'll have to think more about it. Okay. Let's see. We're now going to talk about the program S.A.G.E. We're going to, have I got the right things up? What happens if you take them? What happens if you go to the next? Oh, you're down there? No. Is that where you are?
I'm at 148.
148. Yeah. What happens if you go ahead? I'll go down 1. Do we have a description of S.A.G.E? Yes. Good. That's good. Okay. So this is the point about S.A.G.E. The goal was to assess the association between a quantitative trait, it can be qualitative as well, but let's talk about a quantitative trait, and covariance in a pedigree. That was the whole point. And then we said, well, the covariance, one of the covariates could be a marker. And it could be, and they could be transformed into using the marker specific derived variables. But you know what a lot of people do in association analysis? They they adjust for age and this and that and the other. They take this adjusted thing and put it with their markers. That doesn't make any sense. You've got to do them jointly. There's a real problem in doing it separately. So the idea is you can put in all the age and anything you want plus this marker, okay? And it's a marker that you can call, if you want, dominant, recessive, additive, or whatever you want. So you can also, and this is the neat thing about it now, you can use the transmitted allele indicator, which it'll find for you, as a covariate, and you'll be doing a TDT type test. That wasn't one of the main reasons for the program, but you can do it. The main goal was just the association between a quantitative trait and covariates and a pedigree. And then we realized, well, you can put in all your markers, which is what you want when you've put in other things as well, such as age, sex, and blah, blah, blah. So it uses a regression model with transformation of both sides. And the idea is you want to transform it to get approximate normality of the residuals. By transforming both sides, as I've said before, you get median unbiased estimates of all the parameters, which is nice. And you may say, well, why not mean unbiased? Well, they're not, they're median, which is good though, because if you think about it, you really, in a way, median unbiased makes more sense than mean, especially if you have a very weird distribution. And you have a very flexible correlational structure. In fact, we started off with a very strict, then we said, hey, you can put in any other correlations you want. And that is possible. But the main correlational structure is what we might expect in pedigree data. And this, don't forget, we are using pedigree data. We're not using just individuals or nuclear families. But you can combine pedigrees of any size, even of size 1. So you don't, I mean, you can have independent individuals as well. You can both in. You don't have to have, I mean, the idea was to use the information in pedigrees and with a correlational structure, but you can put both together if you want. And you can use for the analysis of density space SNP data, including 500K or million SNP genome-wide association scans, whatever you can do that. However, to make it, I mean, originally it was just for 1 or 2 markers and maybe a dozen markers or so. But if you are going to have all these SNPs, say 1 million SNPs or more, 500,000, then you need ways of speeding it up. And there are ways of speeding it up, which I hope we'll get to. So let's look at the residual variances. So we have some variance components. And the first of these is the polygenic variance, okay? Then we have the marital variance. We have a component that asks how variable, it's what proportion of the variability of the trait after allowing for all these covariates, what proportion is, as it were, a marital correlation. It's a marital father-mother. And then you can have a sibling variance, okay? In other words, there can be a sibling variance in addition to anything else you're regressing on. So this allows for the fact you may not be regressing on all the things that make SIBs environmentally similar. You can also have a nuclear family variance. And this is the interesting thing. If you think about it, every individual belongs to 2 nuclear families. They're either a child with 2 parents, or they're one of the parents with a bunch of children. So you have 2 of these in a sense. All right. So it also allows for individual specific variance apart from random error. Okay. And it wasn't meant to, but then we said, well, why don't we let it estimate heritability as a polygenic over the total? Now, some of you may know that I'm not a keen estimator of heritability in human data. I think that was obvious on day 1. But we said, hey, people want it, so we'll do it. All right. Let me, all right, let's go on. And it estimates residual familial correlations. Okay. So because you've got these variance components, you can take the right variance component divided by the total variance and you get familial correlations. These 3 are class specific, the sibling, the nuclear family, and the individual specific. They're basically, it's class specific variables. And so what do I say about that? They're like intra-class, if you like. Now, you can also, and this came much later, you can add a transmitted allele indicator. And if you've got a transmitted allele indicator, you can not only do TDT, you do what some people call QDT, a TDT for a quantitative trait. So that's obtained using derived variable expressions. And when used as the prediction variable in the regression analysis, the results is TDT type analysis. So you've got all these were added on later, but they're all in the same framework of large pedigrees where you want to model as closely as you can the correlational structure, so you can tease out what is genetic, what you hope is genetic. So the transmitted allele indicator, you can see it's one of these functions, and you say you want the covariate for each. You can say for each allele, you can determine which is the first allele transmitted and which is the second allele transmitted. And you have to say how your alleles are in the data. For example, you have to say there's an allele delimiter, and you can say what your missing alleles are. One of the things you have to realize about S.A.G.E, it was meant to be very general. Some people think too general, so that you're not limited to a particular input style. So if you look at this, you'll see that we have the family number 1, individual number 3 has a P1 and a P2. And now parent 1 and parent 2, sex of the parent, IDDM, whether this is this disease or not, and then you've got these markers, and they have you can see they are what's called the 1-column format with an allele delimiter. And given all that, the program can calculate using this function as we got down before, using those expressions, and they do all that for you if you say you want it for every marker. Okay, and there you have it. This is what it looks like. You can see in each row, well, we haven't got the whole row, but there is either an allele delimiter, a transmitted allele indicator or not, and you can see that for these various markers. You can have other marker functions. For example, as you can see, you can have the call it an additive marker. You can call it in this case, you could say recessive marker. You could have all these other expressions as well, other marker functions. You can use all the marker functions in S.A.G.E. Okay. Let's consider binary traits. Now, the binary trait is modeled by the logistic function. It's y equals 1 for affected, y equals 0 for unaffected. And what we do is we look at this mu sub I, this thing that it takes the place of the mean, and all the covariates go into the logit. Okay, that's what that means there. Okay, and it's going to be, if y is 1, then you can have all these covariates. If y is 0, then you see from the mu I doesn't depend on the covariates. All right. The logit is assumed to be normally distributed. Okay. However, and I think you'll find this in the manual, and there was a paper, oh, I forget who wrote it, it's in the manual, came out, oh, I don't know, it may be 10 15 years ago. It was rather beautiful in that it showed it really doesn't matter. You don't have to transform. So there is no transformation for a binary trait. It's really completely unnecessary. So it says it's a student we normally distribute. You might think, well, we might have to transform of that. No, it's not essential. It's remarkable. All the covariates are first centered, and then the residual variance components sum to 1, just to standardize everything. So now you can get the intra-class correlations by putting a particular variance component on top, just divided by the sum. Well, since you've already summed them to 1, that's okay, it's done. So this is the program, and it estimates the association between a dependent trait and independent covariates in pedigree data. Now, this is independent. Hold on, this is independent in the statistical sense that I don't like the word independent. They're not necessarily independent at all. But we talk about those, talk about the dependent variables on the left-hand side of the equation and the independent ones on the right-hand side. They really predict a covariance, okay, to estimate the familial variance components and heritability. So we've got a demo coming. So it's going to be the older DBH data, 4 families, and we're going to use the option square root of DBH. We're going to this is a quantitative trait, so we're going to transform it. We're going to, because what we're trying to do is get normality, we're going to use the George and Elston transformation. Remember, if you want to try and get normality residuals, this transformation will give you approximate normality for the most peculiar distributions if you look up the paper. And we're going to put in 3 covariates, family 1, family 2, and family 3. We've got 3 families, and we're going to put in covariates for them. And actually we have 4 families, and we only need 3 covariates for 4 families. I hope that's clear to most people. So we're also going to use the presence of the A allele at the ABO locus created from a derived variable expression as a test covariate. In other words, we're going to ask, is the presence of A significant, does it have a significant association? So I think you take over now, do I? No, so let's see. All right, let me do this. For analysis, we use the DBH data. We're going to use square DBH trait started with the familial with covariates FAM1 and FAM2 and FAM3. There are 4 families, so you don't need 4 covariates, just need 3, because the 4th family is absorbed into the intercept. We also create a covariate using function which indicates the presence of the allele A at the ABO locus. So this is, we have in the data, we've coded these phenotypes as follows. If you see in the data phenotype 1, then we say these are all the genotypes that have an A1 present. Yeah, and no B present. The phenotype 2 is the A1B. Phenotype 3 is saying is A2 as a dominant, as it were. 4 is the A2B, and 5 is the BBO, that's like dominance, and 6 is 0, 0. So this is how we've coded them, because we want to know if A is present. We're going to want to pool, I suppose, the phenotypes 1, 2, and 3, 4. Anyway, we'll see that as we go along. So take it away, Yunju.
First, I will show the couple of slides and then probably go to like a live demo. As you can see in here, that the way that we specify, just like the Dr. Elson was explaining, that, you know, using the tool, creating the new variables from right here, you see that we want to actually create a new variable called A-press, okay? And then using the ABO marker data, which we recorded as a 1 to 6. And by doing ABO value less than 4, we are creating a binary covariate says 1 or 0. And then we are going to test this one against others, okay, against our like a main square root DBH trait. That's how you create first. And then now in trait, we want to specify our trait to be the square root DBH, and then we want to add a covariate, which is like a FEM1, FEM2, FEM3 by like clicking the covariate down arrow, and then find the FEM1 and add a covariate, FEM2, add a covariate, FEM3, add a covariate. So now we have 3 covariate added in there. Now let's go add one more, which should be our A-press covariate that we just created using the creating new variables from the existing value. So this is how you do it. In the covariate list, we select A-press, and then this is the where that we are making sure that this is the covariate that we are testing, okay, against the main traits. And then rest of the covariate in FEM1, FEM2, FEM3 are just in a kind of regular sense. That's not the testing covariates. Okay, that is still in the model, but just covariate. This is the way that we are making sure that this is the test covariate. Then click OK. Okay, now so all those covariates and traits are specified, and we want to see the transformation is correctly specified. Right here, by default, it actually does have like a George and Aston as the default transformation. If not, we can make sure by clicking the down arrow and then click the George Aston options right there. And then if you want to change anything, you can actually change. In this case, we are fixing lambda 2 to 1, and then lambda 1 will be actually estimated. We are not fixing it. Now all the covariate and traits are ready, and then making sure that we have the right variance component specified. We are not allowing any averagings that actually allow like a mean specific imputation. We don't want to do that. We want to use the covariate value as it is. And the variance component, so we are estimating the polygenic components and the marital and the sibling.
If I may interject,
yes,
I don't remember these data in detail, but my guess is that if we tried to estimate the family component, it probably blew up, and that's why it's not there. I don't really know.
Yeah.
But typically, you might want to estimate all of them. But for some reason, we decided not the family. I suspect it must be, you know, if things blow up, then that means you've got too many parameters. And so I suspect that's what happened.
Yeah, I mean, you can still specify to estimate all of them instead of blowing up. In a sense, what Dr. Elston mean by blowing up is actually when you are trying to estimate too many of them, then it will actually put the one of them that is close to 0 to just fix it 0, and then go on to the rest of them.
Right, right. Yes, that's right. It does do that.
Yeah, but usually I think usually family, the component, and the sibling component, you know, they unless you, I think it's a specific the pedigree structure that you have, unless you know, it's, you can estimate both. You usually want to do one of them.
Yeah.
And then now I will go to the live of this one if you'd like to see it. I think I will just skip and just go on maybe to at the end if we have the time. What about that? You want to see it now or after it's done?
Oh, okay. So we have an output here, and it gives you the analysis description first. What what you're the primary trait. It's now allow averaging. That's an interesting thing. Sometimes you have a lot of missing values. And if you allow averaging, you can basically, it says, okay, just put the average for the sample for the missing value. So this is a good idea when you're doing a whole bunch of markers, and you've got to, you want to do that. But if you do that, you've got to realize the results are wrong. But when you have, let's say, 10,000 markers or 100,000 markers, you may decide, well, I'll just pick the top 10,000, say, out of 100,000 with this, and then I will not disable it. I will not enable it. I'll disable it to do a correct analysis. But the idea is to get an approximate analysis for all your markers, and then pick out a large number that's very suggestive, and then do a proper analysis. That's one way of making the whole thing go faster. All right, limit output disabled. Okay, the output would include complete model information. A lot of information. If you're doing a lot of markers, you'd get completely lost in that. And it says omit complete summary table. No, we want to look at the complete summary table. We want to see what's going on. And you can display summary table by order. You want to do them by the likelihood ratio test p-value. The most significant ones you want to look at first. And you may show no more than 10 results, whatever you want. All right, but those are little things for making things go faster when you've got a vast amount of data. We're going to use the Lorton-Nelson test. Typically, you want to fix lambda 1 at 1. You could put it down to -1, I think, but you could no lower. Lambda, sorry, I've got the wrong way around. Oh, we're fixing it, so because we have square root already, I see. And lambda 2 is fixed. Okay, so we're not going to transform. And then we've got the various, if we were transforming, those are the main parameters in the model that would be, that model includes the intercept fam1, fam2, fam3, and A present. That is what would be transformed, but we're not transforming. And it says non-transform components. When apparently we are transforming the components of it. No, we're not. We're not transforming anything. So here you see the A present test. We have the intercept. We have the three family coefficients in their regression model. A present. The estimate is 0.08 with a standard error of 0.14. So of course it's not very likelihood. However, I may stress this later. Look at these two values. You've got the Wald test and the likelihood ratio test. The Wald test is simply the estimated divided by the standard error and referring it to a normal distribution. The likelihood ratio test, though, is a true likelihood ratio. The Wald test goes much faster. So it's another thing you could do is you could say, for example, do only the Wald test first for if you're doing millions of these things, and then pick out I don't know, maybe the top 1%, 10%, whatever. And then at the end, what you want everything is by the likelihood ratio test. But the Wald goes much, much faster because it's all done under the null hypothesis, those of you who understand the Wald test. All right, and then it tells you if you've got an asterisk, it may not have converged. And now the bottom, you've got the summary table. So That seems to work well, not very informative for us, a p-value of 0.55. Anyway, let's go on. And, oh, these are, this is, it tell you you've got the analysis description first, and then second, you have the transformation configuration. And last of all, you have the complete summary table. Okay. And the test covariates, and there you see the last value. I did that just by looking at it, but now I see they come up as blocks. Okay. So now you have some sample description. You have 923 individuals. You have 4 independent, well, assumed to be independent pedigrees, because you have four constituent pedigrees, in which we assume to be independent, and no singletons. The number of constituent pedigrees with complete information, all the marker information, is only 494. Note, missing data replaced by averages are considered complete, but we did not allow averaging, as I recall. So down the bottom, you've got each covariate, you've got its standard error, you've got the standard deviation, you've got the minimum value, maximum value. Okay, so let's look at the maximization results. We, first of all, the first thing I like looking at is the last column. Remember, we're doing maximum likelihood. The derivatives have to be 0. And they're pretty close to 0. That looks pretty good. That's the one I look at first, because if any one of these is not 0, I stop. All right. Now, the variance, whoops, I'm way off here now. Hold on a minute. I'll be here. The variance components are the first thing. You can see what they are, and you can see that they you see the p-value for them. The random one is I suppose p-value for that, but the most interesting one is the polygenic is very significant, sibling slightly significant. The next box we have tells us how we calculate the polygenic. We're using the heritability, we're taking the polygenic component and we're dividing that by the total variance. And that gives us a heritability. Now, of course, as you know, there's lots of assumptions underlying that, but we'll just gloss over that. Next thing, you look at the bottom, you can see the familiar covariates. You can see, well, the family 1 might be slightly significant. Otherwise, they're all pretty not significantly different from 0. Transformation was fixed because we already had square root data. And then on the right, I would look at that first, but that's just the way I am. I don't look at that last, because if those are not all close to 0, there's really no point in looking at the rest. All right. So when we do a likelihood ratio test, it has first of all, you've got the likelihood without the test covariate, which in this case is the presence of A, and you've got the likelihood with the test covariate, and that's, you see those two likelihoods. We look at twice the likelihoods, the difference, and we see it's 0.38, and it's 1 degree of freedom. We're just testing one thing, and the p-value is 0.55. Okay, so let's look at an example, an additive model for SNP genotypes. We're going to use Illumina 4 SNPs. They're coded as in the 1-column format, and we're assuming only 2 alleles at a SNP. That's pretty usual. I've got to warn you that you can have more than 2 alleles at a SNP, but they're pretty rare. Currently, the SNPs must all have the same coding. We need an additive model for SNP covariance. So we'll code 1, 1 as 0, 1, 2 as 1, and 2, 2 as 2. That's as additive as you can get. 0, 1, 2. You could put -1, 0, +1. You do all sorts of different things, but that's how we're going to code it. Alternative models, we could say recessive, and that will say that only the 2, 2 is the one that shows up. The 1, 2, and the 1, the 2, 1 they don't have any affection. I presume that's what we're looking at. If it was dominant, you could have a recessive or dominant. Okay. And now, okay, you're going to take it over from here, right, Yunju?
Yes. Next, I will go over the slides that how to create those additive coding within GUI. Just like we talked about using the creating new variable, that's the tool that we are going to use. Just the click tool, create new variables, and then we get this the new window right there. So we click add, and then this pops up. Then we click the functions right there. Okay, and then make sure that we are using the marker. Okay, so this will apply to all markers in the marker list. And then we are making it as a covariate type. And then we just type in this one. Okay, so name, so this is a regular expression kind of way. So this name will be replaced with the old marker, the SNP name in this case. And then using the allele tool, whether it has the allele 2 or not, so then it will become like a 0, 1, 2 coding, since it is the additive model, additive coding that we are using. Then actually that brings back to the output. So it is the parameter file that it look like.
So this saying of batch is exactly the saying as putting all that in for each covariance separately, or putting in each marker separately. And the model we're deciding additive each time. So that's and then you see it says a name for each of your markers. When you see that $sign name $sign, it's just a token, and in the output you will get the actual name. I think that's, and we're saying we have a polygenic effect. We have no family effect here, no marital effect. We do have a subship effect. That's what we said in this particular thing. And you'll see on the next slide, you'll see they have the wall test and the next slides, Yunju. Yeah, you have the wall test and the likelihood ratio test. And if those two test statistics are very different, well, first of all, you have to understand that asymptotically they're the same. So if they're very different, this suggests you're not really large enough sample size. But you can see how they differ. If they don't seem to differ that much for these, but if it were a question of very significant, and one of them was very significant, the other was not that so significant, basically that's telling you your sample size is not large enough for the asymptotics to kick in, because asymptotically they have to be the same. And there we have the batch mode again, and it's saying without test covariance. You can see that. And we have similar output. I don't know, anything else to say? I don't know. And then you have another one, you've got the variance components coming out. the other parameter, total variance, intercept, all these things. And then you've got a joint test at the bottom. And there again, it's not that very significant. Okay, I don't think it's, so you've got lots of different output options. So the output, you can filter it. You can say list all test covariates, list only those with a likelihood ratio p-value less than some specified value. You might, first of all, it depends on how many tests you're doing. I mean, if you're doing 1 million tests, maybe you only want to see those that are significant about the, I don't know, p less than what, 10 to the minus 6 or something, or whatever. And you can list only with test covariates if the wall p-value is less than some specified value. You obviously don't want to look at all the results, it'd be far too much. You can say only the first 10, first n test covariates were list ranked by p-value. You could say that, or the first 20 or whatever, and list only test covariates with a likelihood ratio test wall p-value, like the less than some specified value, one or the other. I don't know whether you can, probably both, I think, as well. If all is specified, then any others are ignored. Okay. If any combination is specified, they are applied jointly. You apply them all. In addition to filtering, test covariates can be ranked by wall p-value, like a ratio test p-value, or the larger of each of the two, whichever way you want to do it. There's lots and lots of possibilities, and these are made for you to do some filtering, because if you have millions of markers, you first of all want to maybe narrow them down before you do anything else. Okay. Specifying any of the above ordering schemes will produce a separate summary file. Okay.
So before we go to Decipher, there is a question. So in the association test, is the program considering every pairs of samples as the unit of a Y measurement? In another word, how is Y is defined?
Ooh, wait a minute. Y is a trait. There's nothing to do with pairs here. You look at the whole likelihood for the whole pedigree. This has nothing to do with pairs now. You look at everything, and you have to, you're modeling all the various variance components. You're modeling a regression equation, which maybe you're transforming or not. So you have to go back to the whole Elston-Stewart algorithm to do the likelihood for a whole pedigree. And then when you've done it for the first, you get the log likelihood for the first pedigree, then for the second, then you add up those two logs, and then you add up the log likelihood for the next pedigree, and so on. This is pedigree analysis. There's nothing to do with pairs. So if you really want to understand pedigree, there's two basic papers. I don't say they're easy reading. There's the original Elston-Stewart paper, and then there's the Severtson, which I forget who, I think Severtson is the first author, then George and Elston. I think that's what it is. And that's the paper that has all these familial variance components in it. And the other thing is you can say, okay, I want to define classes, and I want to make up my own variance components. Anything that's common to all these things, you can do that. It's extremely general, but please don't talk about pairs. This is pedigrees. Remember, the original purpose of S.A.G.E was to look at the likelihood of a whole pedigree, and that is very important. Have I answered the question? I hope I have.
Yes.
Thank
you. Yes, I was confused because
Well, it's very easy to be, don't have to apologize. The first time you learn anything, you get confused. This is par for the course, as they say.
Yeah, if you,
right.
I may ask another question. So
Please.
So this is related to linkage, right? Not association, because we just talk about TDT.
Right.
And this is actually target at the linkage signal.
This is association, but remember, we can put a transmitted allele indicator in it, which would only it will only find association in the presence of linkage, or linkage in the presence of association. We can do that. Everything we did for TDTX, we can do now in S.A.G.E by creating a transmitted allele indicator and putting that in as a covariant in the equation. Okay.
Yeah. Okay.
That makes sense.
Yeah.
Yeah.
Thank you.
Yeah, sure. No, please. I do like these questions because I'm sure you're not the only one who was a bit confused. Lots of, I mean, I remember Joan Bailey Wilson saying you have to take the SAGE course 3 times before you understand it. And I've taken it more than 3 times, so I think I understand it. At least I've
Thank
taken
you.
it
So
more than 3
true.
times.
And I'm still learning new things, Robert. And I
Good
helped
for
you
you.
design this whole thing.
I know you did. I know. Oh yes. Believe me, I know.
I'm still learning new stuff, but yes, it's like every time you listen to Robert talk about this stuff, you learn something new. You go, oh, I didn't get that the first time.
Yeah. Well, it's difficult. We're going pretty fast, and that's because not enough people are asking questions. Ask questions, and if we were doing it live, I'm sure people would ask questions, because I'd be there walking around looking at people, staring at them.
Right. You'd make us ask questions.
Right. Yeah. But when we're doing this on Zoom, you don't have that option of talking to individuals and looking at them with piercing eyes. Do you really understand? Okay. Decipher. We're probably going extremely fast but that's good. Please do ask questions. Decipher is a remarkable program. And this was, I don't think you could have been involved in this one, Joan, because this was.
No, I'm here because this one's new, Robert.
Right. Well, it's new to you.
I mean, new to me. Yes.
Right. This was Katrina Goddard's idea. And the generality of it is amazing, and you have to read the manual to see how it works. And I remember when she wanted to do something, and I said, you do this, and she said, oh, this is analogous to this. And so we'll see one slide at the end. I'm not sure I can talk about it. I'll try. It's got so much you can do in it, but the main point is haplotyping. That's the main point of it. Okay. It's a tool for the analysis of fine-scale molecular genetic data. And it's so fine scale that you really got blocks that you want to put together. That's what a haplotype is a bunch. It's a bunch of a little bit of chromosome segment, all the same chromosome, individual chromosome. It's used for disease locus mapping. We want if we can get the haplotypes first, we have much more chance of mapping these locus. And it infers population history for a region. It can do that. Remarkable what it can do. So what is a haplotype? Haplotype is a set of alleles across a specified number of loci existing together on the same individual chromosome. And I always remember we have pairs of chromosomes. This is all together on the one. It's analogous to allele for a single locus, but instead of, it's a string of alleles that go together as a block. So why not use it? Okay, they're so close together that they get transmitted as a block. That's what you're trying to find, is these haplotype blocks. Okay, there's a whole literature on estimating haplotypes, and you have to see some of it, and if you know some of it, oh, there are such problems. Well, this is wonderful. It looks at it, allows for a lot of those problems. So a diplotype is a set of two haplotypes. In other words, phase known. I mean, I don't know that anybody uses the word diplotype, but I do. So for a particular individual, a diplotype is analogous to a genotype. A single locus, you have alleles and genotypes. If you have all these chunks, blocks together, you have two haplotypes, make a diplotype. Okay. In fact, I think it was on the first day we talked about phase known diplotypes. Well, by definition, diplotypes have phase known, by definition, really. But a lot of people, I don't know, they had, it's different. You have to understand the backgrounds of different people, how they grew up into genetics. And I know that Newton Morton would always say phase known diplotype. Personally, I think that's just, you know, whatever the word is for too much information. You don't need the diplotype by definition is phase known. Okay. Genotype is unphased or unordered multilocus genotypes. So, you know, we have genotype, diplotype is, you have a lot of genotypes. You can have two locus genotypes, but you can also have two locus diplotypes. And I think I discussed that on the first day. All right, haplotype versus single locus analyses. Consider a two locus system with disease allele bearing haplotype in the middle. You've got this A allele at one locus, then a disease bearing allele somewhere in the middle, and you've got the B allele at another locus. But all these are on a haplotype, you see. There are, so this is what happens. This is a little bit complicated. But what this is saying, if you group the three lower rows of the table, you get 0.6 and 0.75. All right. Now look at the odds ratio. That's going to be 0.5 times 0.75 divided by 0.25 times 0.6. Is those the cross things? And that's 2. Now you have an odds ratio of 2 there. You see that? Because you can group those together, you have an odds ratio of 2. But consider if you had single locus tests. In each case, you have these numbers 60, 50, 40, 50, 60, 50, 40, 50. And then the odds ratio is only 1.5. So somehow you've magnified that. You've got a much stronger association. That's why haplotypes work. Okay? You get this extra boost because if you like, your odds ratio goes up. So that's one way of looking at it. So functions of Decipher. Actually, it's got so many functions. It's amazing to me. Most people just want it for reading haplotypes. So haplotype frequencies can be estimated for specific sets of individuals or pools with the option of partitioning into subpopulations. See, individuals or pools. You can have pooled individuals. Most peculiar. And this is what makes it we used it for pools of data at one point. Pools of you pool the blood and you pool from different individuals, and it can do a lot of separating out. A list of all possible non-recombinant combinations of haplotypes for each individual or pool can be obtained. So you're thinking of as an individual or a pool, okay? A list of the most likely combinations of haplotypes for each individual or pool, together with the posterior probability of each, based on population data. And a like ratio test to compare the distribution of haplotypes between groups or subgroups. So we used it, and you know, I can't for the life of me remember why we had pooled data. There was some reason, and it escapes me. It'll be explained, I presume, the papers in the list of references. It's Quade et al. Quade. who wasn't Quaid at all, but she got married, so she changed to Quaid. That I do remember. I don't remember her first name, original name now. But we were interested in pools of basically DNA pooled from people and separating out. So this is what you have. You either have unrelated individuals or pooled individuals. You have individuals with molecular haplotypes for one pair of loci, individuals with family data. You get it all into a common format. And then what you can do, you can haplotype, or you can find the set of all possible diplotypes. So even from pooled data, you can find out what are all the diplotypes in this pooled set of DNA, if you like. And you can you get the haplotype frequencies, get the most likely diplotypes, and you could do a lot of statistical tests. This is quite remarkable. And I'd say I cannot for the life of me remember why we pooled. There was some reason for it. Oh, I know why. We pooled the data because we were looking for some kind of association. And instead of looking at each individual, we pooled them into groups. And then once you found there was a particular haplotype or particular, you notice something in a pool of say 5, then you would type those 5 individually. So in other words, you did less typing necessary because the figure 5 comes to mind. There were lots of different possibilities, and we showed that most of the general things that come out of a pool of 5 is about right if you want to minimize the cost of typing. So the idea there is instead of typing everybody start off with, first of all, you type pools of 5. Anywhere you find what you're looking for, you type those individually, whether you're looking for an affected individual or what. All right. So this is the Decipher program. It estimates haplotype frequencies from marker phenotypes. That's what you would want it for. But it does do these other things, remarkable things too. Do I consider? Oh, okay. So this is simulated data. Okay, I'll let you take over.
Robert, before you go on, can I ask a question? Does this only work for unrelated individuals, or does it do family-based haplotyping as well? And second question, I may have missed it. How many, how big a haplotype can it do? How many different markers at a time can go into it?
It decides where each haplotype begins and ends.
Okay.
That's a nice thing. You put in certain criteria and it says, oh, well, by your criteria, this haplotype has ended. And we go on to the next one.
So I see here, individuals with family data.
Right.
So it will do haplotyping with families.
Absolutely.
Oh, fantastic.
So general. It's amazing. And I say, and I remember that pooling of individuals. And the beautiful thing is that you could put all these things into a common format, whatever you've got there. And once you've got that common format, you can do the various things. This is a beautiful idea that Goddard had. Beautiful
because most of the programs for haplotyping in family data are not very satisfactory.
I agree.
Yeah, they just are not.
Yeah. Well, you want to try this one. I mean,
we will. We've been looking around for a family-based haplotyping method that will work better than most of what's out there.
I think
so we'll definitely try it.
You have to do certain things like say how many ties how many starting values you're going to start from. You're just like all the others have to do. Maybe they don't. Maybe they just automatically try so many. But here you've got all these parameters you can put in and try. And I think we've done so little use of this program, we ourselves.
Right. But, I suspect it's not used because a lot of people like me didn't know it existed.
That's right. That's right. Well, now I think you'll find this is using some simulated data. We have not had reason to use it, but I just think it was a beautiful idea that Katrina Goddard had, to put all this together and show how you can do, I say, you can do several things, like use pooling DNA when you're looking for, say, an affected individual. Instead of you can pool, you know, sets of 5 at a time, and then do the individual ones, and save a lot of money on typing. And the
Yeah, well,
reason
people were doing a lot of that in the early days of
Right.
of GWAS genotyping and of sequencing,
yeah,
because it was so expensive.
that's right. Now you don't need it for that, but you can use it for this, and it will decide how long the haplotype is on the basis of certain values. I think there are some pretty reasonable default values, but you can change them and see what difference it makes. Yep.
Sure, because, you know, HaploView works great for unrelated individuals. There's tons of haplotyping programs that do decent jobs for unrelated individuals.
This isn't related.
Right, but when you want to do it in a family to take advantage of the familial relationship, that's where most haplotyping programs fall apart.
Right. Now, my guess is, though I haven't looked at it in detail, that if you have large families, it may take a little longer to compute. I don't know, but it would be well worth investigating. Okay. Yep.
Yeah, definitely.
All right. So let's go straight to the demo. So the demonstration. Yeah. Thank you, Yunju.
Actually, I have to be honestly say also that Decipher is one of the last program we added into the S.A.G.E packages. So I am also, in a way, saying that I am least familiar with the Decipher within S.A.G.E packages.
Well, me too. And as I say, when we started off, it was just a way of saving money. When you're typing want to type a whole bunch of people, and you really want to find out, say, who's got a particular mark or what have you, and that's what we used it for originally.
Yeah. Yep. So that is the reason that one of the reasons that this Decipher is like a program that is least used within S.A.G.E as well, because it's the most recent additions. So I will just go through the one that actually
excuse me, Yunju. Yes. It was the latest edition, but let's face it, it was there 10 years ago.
Yes, of course.
That's when we last did any new S.A.G.E
exactly
programs.
More than 10 years ago. Yeah. But since since this was the last edition, there hasn't been much of like a study done using this tool. That's what I was trying to say. Yeah. Sure. Mm-hmm. So we do get this Decipher job by drag and drop, and then this is the program that we need the parameter file and the pedigree files there. And also, since we are doing the haplotyping using the marker data, we also want to add the locus description file as well as like a genome map file right there, as you can see right there. Okay, and then once we have the info file added in, what we do is actually we wanna specify the regions that we wanna do the haplotyping. So this is actually where we are putting in the haplotype block in a way. Okay, so the region will be popped. The list of the region will be popped in from the genome map file. So we have a chromosome 09. If we don't specify the first marker or last marker, then it will try to use everything. But let's say you have like about 1,000 in chromosome 9, I'm sure more than that. But you know, I mean, if you have I would say that if your system can handle and you have like a time to wait for the process, a whole 1,000 of them, probably you can do, but I don't think that is a good idea. So what you want to do is actually you want to specify your haplotype block by specifying which marker within this region that you want to use, and which marker you want to use as a first marker and the last marker to actually specify your haplotype block region. So this is how you actually do this. So you specify your region for the haplotyping. Okay, then after that, we want to specify the different tasks. Since it can do many different things, we can specify what kind of a task that we want to perform. In here, we want to estimate the population haplotype frequency and then gives a cut point. By giving some cut point, it's kind of like making it a little bit faster, because if the one of the haplotype is like a 0.00001, then I don't think you are interested in those. So just making sure, estimating the like a certain threshold, above the certain threshold. So, but you still want to see all the possible haplotype combinations. So you are checking the display or possible haplotype combinations, and then display the most likely haplotype combinations given some cutoff as well. And then you want to do the perform likelihood ratio test and then compute the empirical p-value. And if it's the empirical p-value, you also want to give the maximum permutation number that you want to do, and then same as before, the width of the p-values and the confidence intervals. Then, this is the another one. This is another option that you use, that when you do, if you have like a certain indicator variables that you wanna, if you wanna see the differences between those like partitions, so you can use this partition option. So up to two primary and the secondary partition that you can do it. So to do the primary partition, you just click the define, and you will get the specification window pop up, and then you find whether you want to see the haplotypes within the subpopulation. So it's more like a subgroups within this, like the data that we are putting in. So we want to see the differences depending on this affection status. So you are kind of like a partitioning your pedigree data depending on this affection status. Okay, and then by just, this is the value that you get from your pedigree data, and then you just give the name of it. So you type in, so call it case or affected, and then which value. Since our data has the either A or U, you are saying if this population is individual has the A value, you want to call it as a case population, subpopulation, and then if it's the U, you are calling it as a control population. And then let's say you do have like another partitioning variable that you want to use. In this case, we want to use the sex code, so that within like each case and control, now we are doing another level of like a partitioning, giving the two-way partition. So now we are partitioning even more into fine scale, that male versus female. So that's how you actually specify your partition, and a couple of other options within Decipher. And then you do get this kind of like a summary output file.
Okay, now there's two things I forgot to say. Read the top here. This is completely out of date. It says, remember you have agreed to add an appropriate statement, including the NIH grant number under acknowledgements. And that was true, when was it? In 2008. And I saw that also on some of the outputs for S.A.G.E. They're supposed to be taken away completely. Please do not, you'll have the NIH running after me and putting me in jail maybe if you do that. I don't know. I don't understand what the NIH, but there was a time when if I couldn't show that people used it in there, and and you've got, and the only way I could find out is by the acknowledgements, then they said, well, it's not being used enough, you won't be refunded. Now, if you start doing that, they'll say, you didn't tell us before, we're going to put you in jail, something like that. I don't know what they do when I'm dead. They'll still come after me. Please do not acknowledge these programs anymore. So that I saw that at the top of the S.A.G.E. outputs as well. It's please do not do any of that. Something else now. Oh, the other thing I want to tell you, Jaron, you might want to look in the GUI and there a program called MUGS. Something about, oh, I've forgotten. It's minimum unbroken genotype sequence. Is it
Oh, okay.
maximum unbroken genotype sequence? And there's a reference to a paper and I've had people do it on their on their little iPhones and things, and playing
Right.
around while they're on the, because you can do that on, while they're on trips and things.
Right.
But that would also interest a lot of people, but we're not talking about it. It's only in the GUI. Okay.
Mm-hmm.
So that might interest you too. All right. So this one, the haplotype region is one. You can do a sliding window if you want. You don't have to. There's all sorts of options, and I cannot tell you what is best because we've not tried it enough. It says, do you want to use the 4-gamete rule? No, we don't want it. We want the EM algorithm. The 4-gamete rule blocks, I don't know how well it works. Some people say it works very well, but we decided we'll use the EM algorithm, and you want some convergence criterion. And I forget the details of that. Maybe that's the difference between the likelihoods of successive iterations. I can't remember, but there's something. And then you can say the number of EM algorithm starting states you want. The default is 10. I don't know if that's good or bad. You'll have to look in the literature what people have done and how it works. Subpopulation specified, yes. The analysis unit is each individual. The estimate haplotype frequencies cut off. I think that's saying that when, I don't know, when something is greater than 0.01, you say, okay, I'm on a new haplotype, something like that. You can look at all these things and say, it's been so little used that I don't know, but I would love people to do a lot of simulations first and on real data and see how the various options change. And there again, at the bottom, you've got the width and the confidence. That was, and at the result, it says the markers are in the order M1, M2, M3. That's the result. Now, what happens on the next slide? I'm not sure. Oh, summary output file. So this is, now it's giving you these haplotype frequencies. And in population 1, you can see, and it gives you the most frequent first. You see frequency, the first subpopulation, if you like, is the cases. And you see 211 is the most frequent. And yet, if you look down for the haplotypes in the European cases, 122 is the most frequent. So it gives you all these frequencies, and you can test whether it's that there's homogeneity between these two populations. And if you look right at the bottom, you see you've got an asymptotic p-value of 0.0002 and empirical p-value a little bit bigger on the basis of a 10,000 permutations. Let's see, what do we have next? Oh, here it is. You've got it's all enlarged. I wasn't looking at that one. You can see them all enlarged, and that's basically what you get out of it. And as I say, the cutoffs and things like that, they determine when you say you're at the end of a block and start a new block. Read the manual. It's very readable, this bit. At least you'll see now. And if you know something about things like the four type rule and the EM algorithm, then you can maybe make good decisions. Detailed output gives you, let me see, the possible haplotype combinations in a population. You've got the pedigree member, all these individuals. And I think, I'm not sure what the X's refer to. Is it the most frequent? I think it's the most frequent. It's the allele, that is the allele you estimate, or the haplotype you estimate best for those individuals. That's what I think that is.
Yes. This is the case that for this individual in this pedigree,
Right.
in this population, this will be the possible haplotype for this person.
Right, on the left, and then the most probable one is noted by an X. Yeah.
exactly. And I can say that the reason that this output is like really old is as you can see right at the beginning, it says it's using the haplotype, like the simulated data set, which was used by, I think it's Rob Igo, which I didn't have the file to test it out and update the result file. So that's why the last two, the
Right.
slides of the output file, I couldn't update it. So that's what happens. So that's
Yeah.
why instead of like African American and case control, I just use the case control and the sex, male and female, as
Sure.
just the demo.
Sure.
Yeah.
Next, we have all these references. Now, these references is a complete list of references that include not only what we referred to today, but also in the next day when we look at the theory more. There's all the references as far as I know. If you find any mistakes, let me know. I've been through them several times. So you've got lots of them, lots of them, lots of them, lots of them, lots of them. And then there's some general introductory reading material. These, if you look at these books, I don't think there's one beyond, the latest one is 2003. Oh, that's the Malkin and the book I'm a co-author of. But, you know, you really need to know some of this early stuff. And it's got a couple of papers, I think, down the bottom. Yeah, Fogel and Matulski, and yeah, their book. And I see the last one is devoted to review articles on genetic epidemiology. So you might look at some of those. It's this is a field that has grown from the whole field of statistical genetics and for genetic epidemiology started even before 1900, or certainly around 1900 with Weinberg's work. Okay, now I have a few final words for you. And that is,
Before you do final words, can
Sure.
I ask questions about Decipher?
yes, please do.
This looks, I love that little grid thing,
Yeah,
because you know, you can get family-based haplotypes from several programs, but most of them will only tell you the most likely haplotype, and you don't see
all the
other
others
possibilities there.
Yeah, yeah,
that there are other
Yeah.
possibilities.
absolutely. Yeah,
You don't
yeah.
see all possible haplotypes that may be going on in the family.
Right.
It's very frustrating. So
Yep. Yeah, they'll
let me ask, you know, obviously these are in this data set, it's an example data set, so it's a very short haplotype.
Sure.
What I'm thinking this will be really useful for, and I want you to tell me if you think it's feasible, is
Yeah.
we have linkage studies
Right.
on whole genome sequence data
Right.
in highly aggregated families.
Yep.
And so you get a linkage region. You can't use the multi-point results to help you build the haplotypes because there's so much linkage disequilibrium in your region of interest, in your, you know,
Right.
several
So
hundred variants in a region of
Sure.
interest.
yeah, so it makes sense to make haplotypes then do your linkage with the haplotypes.
Well,
Absolutely.
exactly. And
Sure.
so we do 2-point, and we see what you see, this pile of variants that all have the exact same LOD score, and you know it's a
Sure.
haplotype.
That's right.
But proving that it's a haplotype is another question.
Well, right.
Do you
exactly.
think
Sure.
we could use, you know, those small sets of variants that we think are in really strong LD with each other in this program?
I think so. I
Yeah,
think
and
so.
you said you thought you could go up to about 1,000 variants kind of reasonably if you're willing to take the computational time.
Yeah, it depends on the resources and the
Oh,
time.
I've got
it takes.
the computational resources. That's not the problem. We have a supercomputer. We've got,
Yeah. No, if
the
you
resources aren't the problem. It's software that will do it is the problem. Yeah.
well, I would love you to try out Decipher and
Yeah.
find out how, what does it take? Minutes, hours, days, whatever on your
Right.
computer.
Do we have to, do we have to trim? Do we have to
Well,
make it a little sparse or what? Yeah.
No, I don't think so. I don't think so. I mean,
We'll see.
Yeah, see, because it's been hardly used.
Right.
And you could, set a postdoc or two finding out how this works, how it works best on simulated data and or on your real data. I would love you to do that.
Yeah. Well, we have real world problems that need to do this. And we just haven't found software that, I mean, nobody's been working on family-based stuff. Everybody's only been working on population-based stuff.
I know. But that was the whole point of S.A.G.E in the first place, and then Decipher. It was based, I mean, let's face it, S.A.G.E is based really for pedigrees. That's what it's based on. And a lot of it is based on the original Elson-Stewart algorithm for pedigrees. A lot of it. I mean, and if you haven't read that paper, maybe you should.
Oh, they all, if you are a student on this call, or if you're a non-student faculty member who's just coming into this area, you need to read the Haseman-Elston paper.
Haseman-Elston,
the Elston-Stewart paper.
Yeah.
And those papers that Robert said, oh, these are old foundational papers. You really do need to read them, because the books don't go into detail about the algorithms, and you need to understand the algorithms.
Yeah. So, all right, we're getting to the end. A few final words. So, S.A.G.E was conceived in 1986 while I was working at Louisiana State University Medical Center. Joan and Alec were both there, and it was conceived in 1986. Then in, 1995, I moved to Case Western Reserve University, where it was translated from Fortran to C++, and the GUI was written. If Fortran, whatever it was, 90 or something, had come out in time, maybe I would have left it in Fortran. Ken Lang still has all his programs in Fortran. Fortran's a very good language. Unfortunately, not many people understand it or use it. I mean, I learned Fortran, but I must say C++ is a bit beyond me. Anyway, it was first of all machine translated, then they had lots of problems there. And the GUI was written. So the whole point is there were many programmers, both institutions, who worked on this, many programmers, including Joan and Alexa and many others, and Yunju, of course, most recently. So if you want to show your appreciation for this presentation, I just invite you to make a donation, my honor, at that. You can go there and see. No, I'm not trying to make any money out of this. Absolutely none. It's just if you want to. Originally they were trying to get they were trying to get enough money to get a professorship in my name, a named professorship, but they never got enough money. You have to be clinical to get money from people like that. You have to solve their clinical disease. But anyway, you can do that. It doesn't worry me one bit or the other. One thing that what I meant to say, let me go back to the let's go back to the references. Yeah, I look under Sun X, and I meant to mention this. Can you find those references? Find the one references contude Sun. That's a bit after that one, right? Yes, Sun X. That's it. 2017. Segregation analysis using the unified model is chapter 12 of that book. It's I mean, I was the editor of that, and I encouraged her, she was my student, to write that paper. It's a remarkably good paper telling you how to use segregation analysis. Now, unfortunately, and I'm not trying to get money out of this because I've already been paid for that book. And since they gave me a lump sum, I get no more. But if you can afford to get that chapter 12, I think you'd find a lot of useful information. It was meant for students who actually want to use the program. So I leave that with you. They'll charge you something for that. I don't know what to charge. I don't know. I don't care because I don't get the money anyway. So I just wanted, I meant to talk about that when we were talking about segregation analysis.
Hey,
So,
Robert, can I
yeah?
ask a question about that book?
Yeah.
So what level of expertise is this written on? Is it at the
Okay. So
introductory level, or is it at the Your Got linkage book level?
more like that, but let me explain
that's
to you.
good to know.
But before I say any more about the whole book, let me say that marshalling about, I forget how many chapters there are, 20 chapters, 20 authors to do what they're supposed to do is not easy. And most of them ignore what you tell them to do. I mean, this is ridiculous, but it's meant to be. In fact, let me tell you, the advice I was given is to get postdocs to do this because they are the ones that know the problems. And I tried as much as possible. But, you know, sometimes the author refused to admit that this was meant to help anybody. You know, they wanted to show off. But in general, most of these chapters, although there may be a lot of showing off at the beginning, they are meant to help you use the programs that they illustrate there. They're not all S.A.G.E programs. There's some that are very good that aren't S.A.G.E. So that way the book in itself, I think, is still very useful in that sense. The book, yeah. And they asked me to make a new edition. It was, first of all, there were 3 editors. Now I did that. When they're going to ask me to make another edition soon, I'm sorry, I'm too old. If anybody wants to try, I'll give them your name if you let me know. But it's really meant to be for students, for graduate students and postdocs to understand some of the software that's out there. And you know, a lot of software, maybe half the chapters it is S.A.G.E, maybe, I don't know, but a lot of it is not S.A.G.E, and there are other good programs out there for other purposes. So I'm sorry, I make no money off that. I've made my money off it and I refuse to do it again. So that's it. So any other questions, any final things you want to know before we sign off for today? And then we start again, what was it, Thursday? I think, no, Monday, next Monday. We're going to do more on the theory. And I'll see if I can still do that theory. There's all sorts of bits and pieces that we're going to do. Some may be a repeat of what I said, but that doesn't matter. That's good for you. Some of it, I think, will be new, how some of these algorithms work, and a little. Now, we used to have a 4-day program that wasn't like this, and someone said, "Why are you telling us all this theory? Why don't you put it at the end?" So I did. But really, I do think you need to understand the theory if you're going to use these programs. Okay, any other final questions? So I'll see most of you, I understand nearly all of you are signed up for the whatever we call it, theory or whatever. And that will be on Monday at 9:30. Thank you all. Have a good weekend. Okay.
Yeah.